Hi, I am Luca Bartolomei from Vision for Robotics Lab at ETH Zurich. In this work, we present a full pipeline for multi-robot coordination with an agent-server architecture that allows autonomous robot navigation in partially unknown environments. In time-critical situations, such as in disaster scenario or in search and rescue tasks, multi-robot systems are preferred over single robots, as they can accomplish missions faster. They are also employed in other use cases, such as patrolling, thanks to their flexibility with respect to vehicle fault. For instance, if one of the robots in the team cannot continue, the others can adapt to the situation to complete the task. Multi-robot systems are growing in popularity in the research community, but to have a complete multi-robot solutions, our requirements have to be fulfilled. In fact, coordination between the agents, as well as the capability of co-localizing the robot in the same map, are crucial. In literature, there is still a lack of practical approaches, as unrealistic assumptions are made. Generally, perfect knowledge about the robot states is assumed, as well as known global maps. However, co-localizing the agents in a common reference is far from trivial, as state estimates are also subjected to drift. Additionally, perfect previous knowledge is not possible in general, as only partial information is available. The recent work by Kuznur et al. At FSR 2019 is the closest to the system here presented. There, the authors introduce a multi-robot planning framework for persistent coverage. However, they do not deal with the problem of co-localization. Instead, in this work, we present a complete multi-robot pipeline for unmanned aerial vehicles, or UAVs, that proposes a solution covering both co-localization and mapping, and planning and coordination. Our pipeline is composed of a central server and a team of N agents. We assume some prior knowledge about the navigation area, for example from area imagery. Given this prior information, we select the area of interest, and we assign to all the agents in the team a series of goal positions, which are also communicated to the server. Every agent is assumed to be equipped with GPS, visually neutral sensors, and a wireless module to enable communications with the server. The server performs the most expensive tasks, such as multi-robot sensor fusion and global planning, while on board the agents, only visual inertial odometry or VIO and local obstacle avoidance are required. In the following, we present the pipeline in more details. Assuming GPS and a stereo camera equipped with an IMU are available to every agent, the images and the inertial measurements are used by the VIO algorithm to estimate the ego motion of the robot. The stereo images instead are processed to obtain a local map of the surroundings as a point cloud. These point clouds are compressed and, together with the GPS measurements, the current robot pose and associated keyframes, which include 2D image key points and 3D landmarks from the VIO estimator, are communicated to the server. The server performs optimization-based sensor fusion in the post-graph backend by fusing the sensor measurements from the agents to localize the robots in a global reference frame. Using the results from sensor fusion, the compressed point clouds are used to build a global dense map of the environment, which is used by a hierarchical multi-robot global planner to generate global paths that are communicated back to the agents. This path serves as input to the local planner that generates smooth and collision-free trajectories using the local maps previously built. The same connections are repeated for every agent in the team. Notice that there is no data flow between the agents as all the communication goes through the server. In the following, we focus on the post-graph backend in order to give a better overview of how the sensor fusion component works. We will later focus on the planning components. The objective of the post-graph backend is to localize the agents in the global GPS reference frame W, which is unique across the robots. We indicate every agent type with frame S and the VIO estimate with DOS. This transformation is subject to drift. We model this drift using the transformation TMO, where M represents the agent's drift-corrected map frame. Finally, we use the transformation TWM to retrieve the agent's pose in the global frame W. The same concatenation is repeated for all the agents in the team. The postgraph backend optimizes the transformation highlighted in red to estimate the pose of the agents in the global frame W and to eliminate the drift coming from the VIO estimators. To fulfill this objective, VIO, GPS, and point cloud information are stored in a postgraph structure, where every node contains different elements: GPS measurements, keyframes containing the robot's pose, the 2D key points, and the 3D landmarks, which are later used for visual loop closure, and finally the local point clouds. The point clouds are not used for localization, but they are just anchored to a node to generate a global map after optimization. This postgraph is built incrementally for every agent. Every time a new keyframe is inserted in the graph, a local optimization over the last n inserted nodes is performed. The same procedure is repeated for every agent, where after insertion of a new keyframe, the local optimization is triggered over the last n keyframes. In order to constrain the poses of the robots with respect to each other, we check for visual loop closures over the whole graph. Upon the detection of a loop closure, both within an agent's trajectory and across multiple agents, we perform global optimization. The objective is to refine all the poses and the map transformations in order to get globally consistent estimates. From the optimized pose graph, we can estimate the agent's poses in the GPS reference frame W. Additionally, using the optimized poses and the corresponding dense point clouds, we generate a global dense map using the box-block framework by Olenikova et al. The poses of the agents and the global map are then used by the multi-robot global planner to coordinate the motions of the UAV. The planner computes the path for the agents toward the respective goal position using the RRT star algorithm. To avoid collision amongst the robot, we use a hierarchical approach. At startup, we arbitrarily assign priority levels to each agent. Then we proceed to plan the path for the agents following this hierarchy. In the example, we plan the path for agent 1, avoiding collisions with the obstacles in the map. To plan for the second agent, we consider the no-fly zone around the path of agent 1. The path computed for agent 2 has to avoid both obstacles and the navigation area of all the other agents with higher priority. The planning continues along this line until all agents in the team have been processed and all the waypoints have been reached. Upon completion of the mission, the UAVs return to the respective home position by planning in non-explored space. When a new global path is computed, it is communicated from the server to the corresponding agent, which follows it towards the goal. However, as global paths are generated in the global reference system W, they are first transformed into the local odometry frame O, specific for every agent. Using this rough path, the local planner generates trajectories using the uniform B-spline formulation introduced by Uzenko et al., which considers the UAV's dynamics and performs obstacle avoidance. In the following, we present evaluation of the pipeline. To evaluate the performances of the postgraph backend, we use the IROS dataset. To simulate GPS, we use the available global position measurements by disturbing them with Gaussian noise. In the table, we report the absolute trajectory errors of the estimations. In the first column, we present the performances of VIO only, obtained from the comparison between the ground truth trajectory and estimation from VIO. In the second column, instead, we show the error between the ground truth and the trajectory as estimated by the postgraph backend after optimization. It is worth noticing that the backend is able to reduce the drift in the estimation. In the last column of the table, we evaluate the accuracy of the transformations from the global reference system to the maps frame for all the agents. Given the VIO estimate for one agent, we align it with the ground truth using the last estimated transformation TWM at the end of the mission. This evaluation shows that the error is only marginally increased when compared to the previous results, indicating a high accuracy of the estimated transformations. Finally, we showcase the complete pipeline in a series of experiments in photorealistic simulations of an industrial environment. In the first experiment, we showed exploration of the industrial area using 4 UAVs. The robots and the corresponding waypoints are highlighted with different colors, while the VoxBlocks map is represented as a gray mesh. The waypoints were selected in a lamb-over pattern in overlapping areas of interest. All agents successfully reached the waypoints, discarding any ill-placed goals. During the experiment, we ran the backend and a global planner on the central server, while visual inertial odometry, local obstacle avoidance, and control ran on separate pieces, all connected to the same network. After completing the mission, all the agents returned to their respective home position by planning global paths in non-explored space. In the second experiment, we showcase the advantage of the proposed centralized architecture. Since a dense map contains all agents' experiences, parts mapped by a robot can be reused for planning by another one. In this video, it is possible to see how the red agent plans its path through the alley, which was previously mapped by the green robot. The mission then continues until all agents have reached their respective waypoints and return to their home position. In the last experiment, we present the proposed hierarchical approach for multi-robot planning. Here are the agents with the highest priorities in red, followed by the green and the blue robots. The goal position for the three agents are placed within the same navigation area. The agent with highest priority plans straight-line trajectories, while the other two UAVs have to compute intertwined paths. Nonetheless, all agents are able to reach the assigned goals, avoiding collisions amongst them and with the obstacles in the map. After the completion of the mission, all the agents return to their respective home positions. To summarize, in this work we designed a multi-robot coordination framework for UAVs to be employed in search and rescue missions, dropping some of the typical assumptions made in multi-robot planning literature. We extensively evaluate the system in simulation, where we demonstrate it can guide the navigation of a team of UAVs, ensuring no collisions amongst the agents and with the workspace. Additionally, the source code of the pipeline will be made publicly available at v4rl.ethz.ch. Future research direction will investigate the automatic assignment of waypoints to the agents to minimize the human intervention in the pipeline and how to reduce the dependency of the system on external sensors, such as GPS. Finally, since the computational load in the current architecture increases with the number of agents, we will investigate how to improve the system in terms of scalability.